Hello, my name is Dong-Yun, and today I'll introduce about two algorithms for solving MPC and Sharpie problems in polynomial time. I came across this algorithm while reading a paper about QNN, and I would like to introduce it because it is interesting that it is nonlinear. The main reference is nonlinear quantum mechanics implies polynomial time solution for MP-complete and Sharpie problems by Abrams and Lloyd. As you all know, QNN means quantum neural network. The author of the following paper, which is about implementing QNN, states that there are two difficulties in implementing QNN. The first is about nonlinearity, and the second is about how to learn efficiently. For the nonlinearity of neural networks, the author used the algorithms of the paper I mentioned earlier, and I would like to introduce it. I'll explain about NP and Sharpie. NP is the set of decision problems for which the problem instances where the answer is yes have proof verifiable in polynomial time by a deterministic Turing machine. The problems in Sharpie, the class of problems that can be defined as counting the number of offsetting paths of polynomial time non-deterministic Turing machine. Like other classes of computational complexity theory, Sharpie is a case for function problems, not decision problems, which are generally harder to deal with than decision problems. It's not important in terms of the overall content, so I'll stop here. First, algorithm for MP. First, the algorithm in terms for an oracle which calculates a function that maps n bits into a single bit. We need to determine if there exists an input value x for which fx equal 1. With a polynomial time algorithm to solve this problem, it is easy to solve all problems in the class NP. Indeed, this oracle problems is in fact a harder problem than those in NP because it clearly requires exponential time on a classical Turing machine. Let me explain the algorithm in earnest. First, the first algorithm for the NP problem. Step 1, beginning by performing a half-pi rotation on each of the first n qubits to obtain the state. Step 2, use your oracle only once to calculate fi. If I is solution index, fi equal 1, other fi equal 0. Step 3, reverse the half-pi rotation on each of the first n qubits. It yields the state 0, 0, 0. Here, with probability at least 1/4. For now, I'll skip the reason. What I want to say is that when you measure the previous n qubits, we could get 0, 0, 0 this state for fairly high probability, at least 1/4. After the measurement and getting 0, 0, 0 state as follows. They are very complicated constant, but the main is here, and this constant is just for satisfy Born rule. Alpha square plus beta square equals 0. However, for small s, a measurement of the last qubit will almost always return 0, yielding no information. Because if 0 return, we could not know there exists answer solution. So we wish to distinguish between the case s equals 0 and s bigger than 0. Lastly, step 4, repeatedly apply the nonlinear operation to derive the states representing these two cases apart at an exponential rate. Unfortunately, in the first algorithm, the author did not specify which nonlinear operators is used. They just supposed that it is possible to perform a nonlinear operation on a single qubit that has a positive Lyapunov exponent. Positive Lyapunov exponent means some case could be separate exponentially by time. So author said these two cases, s equals 0 and s bigger than 0, could be separated by some nonlinear operation. Next, to solve problems in the class Sharpie, we need to determine the exact number of solutions s. In order to simplify the description, authors assume that there is at most a single value x for which fx equal 1. They begin as before with a quantum computer that can perform the unusual quantum logic operation and that can in addition perform a simple nonlinear operator whose form will be described below. We conceptually divide the qubits into n qubits and one flag qubit. The first part is the same as the algorithm I mentioned earlier. Step 1, begin by performing a half-pi rotation on each of the first n qubits to obtain the state. Step 2, use the oracle only once to calculate Fi. If I solution index Fi equal 1, other Fi equals 0. Consider the first qubit separately and groups all the states of the superposition into pair space on the value of qubits to second to nth. So separately think about qubit. For example, here is first qubit, second qubit, nth qubit. So and this is flag qubit. Just think about these two qubits. That is the qubits second to nth defined 2 power to n-1 subspace of dimension 4. Why 4? This 4 means 2 dimensions for first qubit and 2 dimensions for the flag qubit. Within each subspace, the computer will be in one of the following states. Left side. First one is first qubit here, left one, and right one is flag qubit. A distinctly nonlinear transformation n is then applied to these two qubits. This transformation is like an AND gate. It ignores the index qubit and places the flag qubit in the state 1 if and only if either of the original components had the state 1 for the flag qubit. So these upper two cases is case about solution exists, and last case solution doesn't exist because the flag qubit of two cases, first qubit is 0 and first qubit is 1. All of them flag qubit is 0, so it means they're not solution. At these two cases, their solution for first case of first qubit is 1, and their solution if case of first qubit is 0. Step 4, the previous step is then repeated using each of the first n qubits as the index. After each, this step means, last step we think first qubit and flag qubit separately, and next, not this, we think separately this one and other things separately. So repeating it. After each iteration, the number of components in the proportion that have a 1 for the flag qubit doubles. After any iterations, the flag qubit is no longer entangled with the first n qubits. It is either in the state 1 for every component of the superposition or state 0 for every component of the superposition. Then step 5, measure the flag qubit to determine the solution. Thus, if one can perform the two qubits nonlinear transformation n, one can find the answer to a Sharpe problem with certainty in polynomial time and using only a single evaluation of the oracle. It may be objected that the nonlinear operator n appears arbitrary and unnatural. Indeed, it was selected exactly so as to be able to solve the stated problem. However, the apparently arbitrary operation n can be built using ordinary unitary operations and much simpler and more natural single qubit nonlinear operators. So I'll explain how to implement this two qubit nonlinear operator n. First, act on the two qubits with the unitary operator. This transforms the states above as follows. Left one to right one. Next, operate on the second qubit with a simple one qubit nonlinear gate n hat minus that maps both 0 and 1 to the state 0. The third final state is unknown, bars with A, is unknown because we have not bothered to specify how the nonlinear gate acts on the third state. So it is not important, and uh, this this will give freedom to choosing nonlinear gate to us. Whatever the state A may be, we can perform a unitary operation that will transform the first qubit into the pure state 0 while leaving the state 0, 0 in place. The comparison is then in one of the following states. A second nonlinear gate n hat plus is now required that will map the states x0 plus y0 to the state 1. This became this, while leaving the state 0 unchanged. After the gate is up, the transformation resulting from the steps described so far is then. The two qubit transformation n is then easily obtained with a NOT gate on the second qubit and a pi half rotation on the first qubit. Two other nonlinear operators are defined to implement nonlinear operator n. How will they be implemented? If one considers the state of qubit as a point on the unit sphere, then all unitary operations correspond to rotation or reflection of on the sphere. And all such rotation can place two state vector in any particular position on the sphere. They can never change the angle between state vectors. A nonlinear transformation corresponds to a stretching of the sphere, which will in general modify this angle. This is not official figure, but I drew based on my intuition about relation between stretching sphere and angle changing by nonlinear operator. It's not correct, but this slide will help you to understand what I said earlier. So in this case, linear, the angle between two states doesn't change while the states are rotation, but lower two cases because sphere is stretching, so the angle between two states change. In this case, angle increase, and in this case, angle decrease. In more detail, the paper introduces the concept of Weinberg's model. So this model is about nonlinear revolution, but it's so physics. So I'll end the presentation here. Thanks for listening, and this is my references. Thank you.
Okay, any questions?
It's very physical. I know that there is a nonlinear quantum mechanics model. I mentioned it in this slide. The model named Weinberg's model. It is about nonlinear evolution about quantum states, but it was very hard to understand for me. There was some Schrödinger equations and very lots of mathematical equations, so I couldn't explain about it, but I could tell you that there are some nonlinear quantum mechanics. Ah, implementing this. This 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 nonlinear operator n is not so simple nonlinear operator. So the next slide is about how to implement nonlinear operator n with some other unitary operations and some simple nonlinear, much simpler than n, and which is easy to implement. So there are two nonlinear operators to implement n. One of them are n hat minus. So this is operator about this transformation, and there are another simple nonlinear operation. It make it's n hat plus, and it makes this second qubit state to 1. As I said, these two nonlinear operators are easy to implement in real world, but I don't know exact step for that. But yes, it is more simpler than this big N nonlinear operator. So this paper is about how to algorithm using this nonlinear operator and how to implement this operator with much simpler nonlinear operators. Is it okay? Yes. It uses this two qubit unitary operator and other operators.
Saying that this matrix is implemented nonlinearity.
That's operation response. Has some other.
This one is unitary.
So
Yes.
results from there.
Yes. Because matrix multiplication is linear. Yes, so this matrix is just for is used for implementing n. Yes, it's not non-linear, it is linear, but using these two qubits unitary operator and other two simple non-linear operator and NOT gate. Yes, all of using that. So we could make this non-linear operator n. Other questions? I think it is similar with Grover's algorithm.
It's similar to the algorithm.
Some a little bit about changing qubit state for only some of them, and both of them are algorithm for searching solution, but by using nonlinear operator, it is more faster than Grover's algorithm.
What about implementations? Did the team only present this as a theoretical idea, or did they also try to implement it?
This paper doesn't mention about implementing it to hardware, but I think it's not hard because Arthur said they supposed to using some quantum computer, which ordinary unitary operators and simple nonlinear operators are able to use. So I don't know how it be implemented on real quantum computer, but maybe it is not so hard. Yes, just it's circle paper.
So we can use this one to implement this situation function.
Ah, yes. In this slide, I mentioned about this paper, neural networks with quantum architecture and quantum learning. So in this paper, Arthur said these are two issues of implementing Q and N. First one is nonlinearity, and in this paper, they used the first one, algorithm for NP. The name of author are Abrams and Lloyd, so they call it AL algorithm and use it for implementing QNN. To implement nonlinearity of QNN. As you know, neural network use nonlinear functions because it in real neural network there are some nonlinearity. So this one use it too. Other questions?